Hello students, in this video we'll prove the arithmetic-geometric mean inequality using Lagrange multipliers. The arithmetic-geometric mean inequality states that if I look at the geometric mean, the nth root of x1 times xn, that is always less than or equal to the arithmetic mean, x1 plus x2 plus xn over n. Okay, we're going to assume that the x1 through xn are non-negative. In particular, we'll just assume they're positive for simplicity. So suppose that xi is greater than 0 for all I, just for simplicity in my calculation. And I'm going to prove this, and so I'm going to prove this using Lagrange multipliers, and so the methodology is the following. What I'm going to do is I'm going to suppose, so here's the proof. We're going to suppose that x1 plus x2 plus xn is equal to a constant number. I'll call it a, right? And I want to find the maximum. My goal is to maximize this function, which is just the nth root of x1 times all the way down to xn. All right, and so now we're going to use Lagrange multipliers. I'm trying to find the maximum of this function. I'm trying to optimize this function subject to this constraint. So the Lagrange multiplier problem states that the gradient, so let's call this function over here f of x1 through xn, and let's call this constraint over here this summand in g of x1 through g of xn. So the Lagrange multiplier method says that the gradient of f is proportional lambda to the gradient of g, right? And so of course the gradient g is elementary to compute. The gradient of f is only slightly more difficult to compute. So what is the gradient of f? So note in particular that it's a symmetric expression. So what I can say that the gradient of f, is going to be, well, if I do the derivative with respect to x1, this is really the formula x1 to the 1 over n, x2 to the 1 over n, xn to the 1 over n. So if I do the derivative of x1, I'll have a 1 over n, x1 to the 1 over n minus 1. And that's permissible since the x1 is not equal to 0, right? And so I see that when I do this, I'm going to get a copy of f itself, and then I'm going to have a 1 over n in each term, 1 over n, x1 to the negative 1, 1 over n, xn to the negative 1, okay? So that's a scalar, and that's equal to lambda times the gradient of g. That's even easier, just all ones, 1, 1, 1, all the way down to 1. And so my conclusion from this is that what? My conclusion is that if I look at f over n, xi is going to be equal to lambda for all I to the negative 1, for all I. So in particular, what this says, since f is not equal to 0, since n is not equal to 0, this condition over here says that xi has to be equal to xj. Since all of these xi inverses, so in other words, this would say xi inverse is equal to lambda n over f, since f is not equal to 0. And then that forces all of these xi to be equal. So xi is equal to xj. That's what we get for all I and j. So all of them are equal to each other. And so now what we can do is we can look at the constraint equation. So if all of the xi are equal to each other, then the constraint equation is x1 plus x2 plus all the way down to xn is equal to a. All of them are equal, so the constraint will imply that n times x1 is equal to a. So that says that x1 is equal to a over n, okay? And so now this is my critical point, and so all of them are equal to this. So in particular, this implies that xi is equal to a over n. And so now I can fill that in to compute my maximum. Of course, when we do the second derivative, we're going to see what. When we do the second derivative, these negative powers are going to come down. That's going to show that we're going to actually have a maximum. So the second derivative test is going to automatically guarantee that we're at a maximum value. And so what we're going to have over here is xi are equal to a, so let's plug that in. So I have f of what? I have f of a over n, a over n, a over n, a over n is the maximum, is the max of f subject to g equals a, okay? And what is this? This is just the nth root of a over n times a over n times a over n. And that's n copies of a and n copies of n, so it's just going to be a over n. So a over n is the maximum of this function. So let's figure out what that means. So that means the absolute largest this nth root of x1 times xn can be is a, the sum of the xn's, over n. So that's our conclusion now. So our conclusion from this, hence we have that the nth root of x1, x2, xn, the nth root of the product of these things, is less than or equal to x1 plus x2 plus xn, all divided by n. That's exactly what this expression is stating over here, and this is exactly just the arithmetic-geometric mean inequality. This is the AM, arithmetic mean, geometric mean inequality, AM-GM inequality, which is very, very useful in a variety of different contexts. Thank you very much.